Welcome back. This is the day the Lord has made. Let us rejoice and be glad in it. In this video, I'm going to talk about general stuff about electricity. So this is going to be relevant towards some general electricity stuff, conductors and insulators, voltage, current, resistance, and I'm also going to introduce series and parallel circuits in this video as well. I will have a subsequent video which goes into more detail with a simulation to show the difference between a series and parallel circuitry. All right, so first off, again, electricity is a pretty important thing. In fact, the fact that you're watching this suggests that there's some electrons doing some work. Electricity is all about electrons moving around. Now, it's more than that, but for this class here, we can just think of it as this idea that electrons are doing work. Can we make some electrons move? And as electrons move, we get electricity, and then we can get work done. All right, so your whole house is wired with a bunch of copper wires around it, most likely, that are allowing electrons to move through it with relative ease. So we should go back and think about what allows electrons to move. So there's things that are classified as conductors, things are classified as insulators. In general, all metals are conductors, all right, as long as it's not rusty, all right? So rusted metals don't count, but if you're just typical metal, aluminum, silver, copper, gold, those things are all conductors. If you're not a metal, you're an insulator. Now there's a variety of like how good of an insulator you are, like different tiers, but as far as we're concerned, if you're a metal, you conduct electricity, electrons move through you. If you're a non-metal, then you don't. And so when you plug in your vacuum cleaner, that cord that you look at, there's a plastic cord, but inside that cord is a copper wire probably, all right? And so the plastic is the insulator to keep you safe so you can plug it in, and the metal inside is what actually conducts the charge through it. So, and conductors, they let electrons move through it, they let energy go through it. We don't need to worry about that stuff here. Yeah, sorry about that. Salts do not conduct electricity, not as a solid. So salts will not conduct electricity, but if you did liquefied salts, it would. Pure water is not conductive. Again, a big misconception people have is that water conducts electricity, not in a pure phase. But if you put salt into it, then it is conductive. All right. So when we talk about electricity, lots of things we talk about include voltage, current, and resistance. All right, voltage, you should just think of this as like how motivated are the electrons to move. Our houses have outlets that are hooked up to plus and minus 120 volts. So we pretty much have a motivation of 120 volts that we provide for the electrons as they're moving through. All right, the batteries typically provide like 1 to 2 volts of motivation, probably like 1.5 under fully. And some batteries might be more than 1.5, but typically probably like 1.5 would be like a brand new battery. That's the voltage it's going to be providing, okay? Current then is going to be how many electrons actually move. We measure current in amps, so amperes. So how much current actually moves through it. That, again, we're not going to give the actual number of electrons. We're going to, since there's lots of them, we use the unit amp to describe a whole lot of them. If you care to know, 1 amp is roughly 6 billion times a billion electrons. It's a lot. So typically, most household lines will let like 20 to 30 amps go through it before that gets shut down. We'll talk about that in a few seconds. Anyway, then there's resistance. Resistance in this class, you should think of it as like anti-motivation. What resists the electrons from moving? So there's some motivation provided by the voltage that the electrons want to move, and there'll be some anti-motivation. This will be stuff that the electrons have to do along the way, all right? And this results in the voltage going down, the motivation dropping. All right, you can think of this in terms of like you wake up for the day and your battery's charged and you got a certain amount of voltage. And then you look at your to-do list. Your to-do list, that's gonna be anti-motivating, all right? That's gonna result in you losing motivation through the day. All right, different materials and different machines, different devices have different amounts of resistance that result in the electrons losing motivation as they go through it, all right? So the electron's like, oh, I'm going through the vacuum cleaner, it loses some motivation, all right? Now there's a relationship here, an equation that you should be aware of, and it's this one right here. So, and I've rearranged it. Probably the easiest way to think of it is current is voltage divided by resistance. All right, this is all the same thing, but how much current shows up depends on, well, how much motivation do you have? The more motivation, the more current. How demotivated will you be doing this? That's the resistance, the ohms. So how motivated divided by how unmotivated can you be, that equals how much current shows up. All right, so you can rearrange for any one of these 3 variables down here. So I've reorganized them in 3 different ways. That way you can solve for the one you need. So Voltage is equal to resistance times the current. Current is voltage over the resistance, and resistance is voltage over current. All right, so this is the same equation. I just rearranged for you in different ways to help you solve some of the stuff that you come across. Now, in a typical circuit, we have things called fuses and circuit breakers. These things are pretty much their job is to make sure there's not too much current showing up. They're like the person at the door saying, hey, we can only have X amount of people inside here. All right, so there's only X amount of electrons allowed to be going through the line at one point. Typically, that's 20 to 30 amps at your house. And so if it ever goes above that, the circuit breaker is going to trip and it's going to say, no more electrons through here and shut it down. The reason for this is metals don't catch fire, but as more electrons go through a wire, it gets hotter. And so what's that copper wire touching in behind your drywall? Probably some wood. And so if a lot of electrons are moving through that copper wire more than it's supposed to, the copper wire can get really hot, and that can result in your house catching fire. So from the hot metal copper wires touching the wood, that's flammable. All right. All right, there's two different types of current to be aware of. There's direct current and alternating current. Direct current is when electrons go one direction. So if they're just going one way, it's a one-way street. That's direct current. Alternating current is when electrons go back and forth. They can go either direction of the wire, and so they fluctuate back and forth. So typically direct current is provided by batteries. If you have a battery, the battery has a positive end and a negative end. The electron's going to go towards the positive end. All right, they just go one direction. They're not going to turn around ever. All right, direct current will have a constant voltage. It doesn't change. The battery has a positive negative end. It doesn't change. The electron knows exactly where it's going. They have constant current. The current moving through those things is going to be the same because, again, the electrons know exactly where they want to go, and they just keep moving that direction. And therefore, the power is the same too. So for alternating current, again, this will be provided by our wall outlet. It's not always the same direction you're moving. And so what happens is we keep changing which way the electrons go. We provide the motivation here. Then we put the motivation over here and back and forth, and the electrons keep changing their mind which way they want to go. So because of this, for alternating current, they don't have a constant voltage. The voltage fluctuates. So on your outlet, when you plug it in, what happens is, again, you're plugging in two copper lines right there. What happens is the power company switches which one is the positive. And so the electron's like, oh, I'm going to this one because it's positive. Then the power company switches it so the other one's positive. The electrons turn back around. And so then and it keeps doing this. In America, it's about 60 times a second. That's the frequency, 60 hertz. All right, that's how often they switch voltage, being positive or negative. So you should be aware that in America, we use a voltage of 120. Again, if you go to Europe, you might need to have some device to modify your plugins because the outlets in Europe provide a larger voltage than we do. That's just because Europe developed their electricity later than we did. So we have 120 volts as our adopted voltage that we use. In Europe, it's higher. However, for some of your devices, you do hook up to the bigger voltage. So like your dryer machine has a special plug-in that actually hooks up to around 220 to 240 volts. So anyway, current fluctuates because what's going on? Instead of the current being one way, it goes back and forth. And since the voltage and the current are fluctuating, power fluctuates as well. All right, so for a circuit is just saying, where are the electrons going? It's following the path for where the electron's going. There are series circuits, and there's parallel circuits, and sometimes there's combinations of them. For the most part, your house is probably wired in parallel. We'll talk about that in a few seconds. But a series circuit is where every electron has to take the same path. So if you had your voltage, your motivation right here, the electrons will take off, go through our resistor. This is just a fancy looking symbol for ohms, so omega. So here's a resistor. This could be anything. It could be whatever you plugged in. And then the electrons go through that. Then they have to go through another one, another resistor. These guys are in series. Everyone that takes off through this path goes through this resistor. Then they go through this resistor. That's what it means to be in series. In parallel, you get a choice. You can take the top path or the bottom path. You're not going to do both. All right. So you can think of this in terms of like your high school curriculum as far as what your course you're going to take. Series courses are ones that everybody has to take. Parallel courses are electives. And so looking at this last circuit here, we have some series part of it where everyone that takes off has to go through this resistor. Everyone goes for this resistor. But then after that, you get to choose whether you want to take class A or class B. You can take the top or the bottom. So you think of this like, okay, well, everyone has to take biology. Then everyone has to take chemistry. Then you get a choice. You can either choose to take DC bio, you can choose to take DC chemistry. There could be another path down here, DC physics. There's a lot of courses here, anatomy. So anyway, parallel is when you get a choice. Not everybody's going to take it. So some big differences then between series and parallel circuits are this. If you have something in series and you have multiple batteries that add together. So if we were to take another battery and add it into series, that'd just be double motivating the electrons. It's just an extra amount of motivation. So again, I'm going to take a look at these things too in a simulator in my next video after this, but this is just an introduction to this, all right? So in series, voltages add up. So this is how your typical graphing calculator works. You have 4 batteries in there. Each battery provides 1.5 volts. They're wired in series. So what happens is the first 1.5 volts adds to the next, which adds to the next, which adds to the next. So then the battery ends up with having 6 volts of motivation for the electrons. Think about the batteries just providing some motivation. All right, saying, hey, I'm going to give you this motivation. Then someone else giving you some more motivation, and someone else giving you more motivation. It just adds up. In parallel, you don't get to add the voltages together, but you do get more current still. So there's still the same amount of motivation, but you like no more extra voltage, but you get more current. For a series one, current's the same everywhere. So we'll go back up to here. If you compared the current going through this top resistor and the current going through the bottom resistor, it'd be the same. Because think of this like your high school day. Like everyone goes to the first period class, everyone goes to the second period class. The amount of people is the same. All right. So we have 100 people taking this class, 100 people taking this class. That number's change. In parallel, though, it splits up. So if you had 100 people, maybe 50 take the top one and 50 take the bottom. Or maybe it's like 25 here and 75 there. So in parallel, the current's not the same because the current splits up. So here's some more math for us here. In series, resistors add up. What does that mean? That means as you go through the day, all these things add up together to be working against you. Like, oh, I got to go through this resistor and this resistor. So you can think of it like 2 homework assignments. I got to do A and B. I got to do homework assignment 1, homework assignment 2. And so that's going to be demotivating. In parallel, they don't add up, they add down. Why? Because you get a choice. So instead of having to do both assignments, you get to choose to pick one of them. So it'd be like the teacher saying, hey, instead of doing both the assignments, how about you pick one of them? All of a sudden, you're like, wow, because I get a choice, you feel less resistance toward it. All right. If I give my kids options like, hey, you can either do this or this to help me out, they will grumble and complain less and they'll pick something. All right. If I tell them I do both of them, there'll be lots of complaining. All right. So anyway, mathematically, to add down, it's 1 over the equivalent resistance. What does it look like? Equals 1 over add the resistors up on the bottom though. So I'll do some sample questions of that in a little bit, not right now. At the end, the voltage ends up being 0, which means all the motivation gets lost. So electrons are perfect runners as they go through the circuit. They are going to use all their motivation. So that electron going through here, if he had 10 volts of motivation, he will spend a total of 10 volts to get through these 2 resistors. So, and they use proportionally more for the bigger the resistor, which is no different than saying that you're going to use more of your motivation to get the harder things done because it's going to cost you more, right? You're like, oh, this is a hard task. So you wake up for the day, you got your full battery charge, you take off, whichever assignment for the day is the hardest one is going to drain you the most. That's all we're saying. But at the end of the day, you're going to need to recharge again. Electrons, they're the perfect runner though, because what happens is by the time they get to the end, and they spent everything, they held nothing back. All right. Another big difference between series and parallel will be in series, if there's a break, everything shuts down. So in parallel, it's not like that. Meaning this, in series, if all of a sudden we broke the circuit right here and we took out this resistor here, nobody goes through anymore. We've taken away something and the electrons can't get across the gap. In parallel, we'd still have a circuit because if we break one of these things down and take it out, they'll just take the other path. It'd be like saying, well, we thought we were going to offer these options, but weren't able to offer all of them. We still have a couple of the options. So in series, if one option gets taken away, it all shuts down because there's only one option. Everyone has to go through this thing. But in parallel, since you have multiple options, if you take one away, you still got electrons moving through it. All right. Your house is pretty much wired in parallel because it'd be bad if like, oh no, that light bulb went out, all the light bulbs shut down in the house. Old Christmas tree lights used to be like that. They'd be like, oh, one light went out, they all went out, because they were all in series. Now they make them in parallel so that if one goes out, the rest of them keep working. And your house is mostly in parallel because they want, if one outlet is not plugged in, not working, they want the rest of the house still to keep working. All right. I'm going to go ahead and stop this video for now. I'm going to have a follow-up video where I talk about circuits and just show you a couple examples of these things in real life. All right. God's peace.